Hello, everyone. Welcome back. So, today I'm going to be talking about the compound angle formulas. Basically, these formulas can be useful when it comes to proving trigonometric identities, and they can also be useful when trying to find the exact value of something that isn't on our special triangles, if that number of degrees or radians can be made up of things that we do know, things that are part of our special triangles that we can solve for. So, just a quick reminder about our special triangles. There's two special triangles, and they look like this. And then the other one looks like this, pi over 6. There we go. Like that. Okay, so let's get started. And I'm going to give you an example of how you can use some of these formulas to find the exact values of some of these things. So for sine 105, well, 105 is not on our special triangles. However, 105 is a combination of 60 and 45. So we could argue that this is the same thing as sine of 60 plus 45. And then based on this addition formula here, sine of a plus b is equal to sine a cos b plus cos a sine b. So therefore, this is equal to sine 60 cos 45 plus cos 60 sine 45, right? And that's equal to, well, let's see, what's sine 60? Well, 60, let's remind ourselves that 60 is the same thing as pi over 3, right? So what is sine of pi over 3? Pi over 3 would be opposite over hypotenuse, which is root 3 over 2. Okay? What about cos 45? Well, that's going to be 1 over root 2. And then plus, well, what's sine 60? Or sorry, cosine 60? That is going to be 1 half. And then sine 45, which is same as sine pi over 4, is the same as 1 over root 2. So what's the answer? The answer would then be root 3 plus 1 over 2 root 2 if we combine those. And that's our exact answer. So very good. All right, now what is cosine of 15 degrees? Well, cosine of 15, let's think about that. Well, 45 minus 30 is equal to 15. So that's equal to cosine of 45 minus 30 degrees. Okay. And that is equal to cos A cos B, right? So cos 45 cos 30 minus sine 45 sine 30. Now, what's cos 45? We already answered that. We answered it earlier and we said it was 1 over root 2. And what's cosine of 30? Oh, we didn't answer that earlier. So cosine of 30 is, well, 30 is the same as pi over 6, right? So what's cosine of pi over 6? That'd be the adjacent over the hypotenuse, which would be root 3 over 2. And then minus sine 45, which we already answered that. We said it was 1 over root 2 times sine 30, which would be, let's see, opposite over hypotenuse, which would be 1 half because 30 is the same as pi over 6. So that is a half. And that means our answer would be, oh, I did this. I should have put plus here. My apologies, because I was following this one. I should have been following this one here because it's cos A minus B, not plus B. Okay, so then we're going to get the same answer as before, which actually is what we expected if we think about the relationship between cosine and sine. That does make good sense to us as to why that is. So that's good. Awesome. All right, and then now we have a tangent of negative 5 pi over 12. Well, let's see. Well, negative 5 pi over 12 is the same as negative pi over 4 minus pi over 6. And that looks suspiciously like two things in our special triangle. So therefore, we have tan negative pi over 4 minus tan pi over 6, right? Because we're using this formula here now, over 1 plus tan negative pi over 4 tan pi over 6, like that. And what is tan of negative pi over 4? Well, tan of pi over 4 is 1 over 1. So this would be negative 1, right? Because this goes into our C quadrant, right? If we just think about where it would be on the terminal angle, it goes into our C quadrant, our quadrant 4, which only has cosine as positive. So this would be negative 1. And then we have minus tan of pi over 6. So what's tangent of pi over 6? That is going to be the opposite over the adjacent. So that's going to be 1 over root 3, like that. And then we're going to have over 1 plus tangent of negative pi over 4, which we already answered that was. We said it was negative 1. And then tangent of pi over 6, which again, we already answered what that was. We said it was 1 over root 3. So our answer is negative 1 minus 1 over root 3 over 1 minus 1 over root 3, which is negative root 3 minus 1 over root 3 minus 1. And there we go. Awesome. Okay, let's move on to example 2. It says to simplify these as far as possible, and we're going to need to use our angle formulas, our compound angle formulas to solve this. Okay, so for the first one, I see it's sine something, cos something else, minus cos something, sine, something else. So which one of these lines up with that? Well, I think this one might. Let's make sure. So sine A, if A is 2x, and then cosine B, right, if B is x, and then minus cos A sine B. So yes, it would be this. So therefore, it would be this one where we have sine 2x minus x, which is just going to be sine x. So this whole complicated hullabaloo thing just simplifies to sine x. Isn't that astonishing? Like that's not something we'd guess, but yes, based on that formula, this is sine x, right? Based on sine A minus B from our original. I'm just going to put that up here so we can refer back. This next one also looks like it would be sine A minus B, except we have a plus here and not a minus. So maybe that would be plus B. Yes, that would be this one up here, actually. This one right here, because we have a plus. So let's do that one. This one would then be sine pi over 4 plus pi over 12, which is sine, let's see, 3 pi over 12 plus pi over 12 equals sine 4 pi over 12, which is equal to sine pi over 3, which is equal to root 3 over 2. So there we have it. Okay, what about this next one here? We have, let's see, cos, and sine. So that means it's something with cos. And we do have a minus or a plus here. We have a plus here, which suggests that it's this one. Okay, so since it's cos A minus B, when I should write what this one was sine A plus B. Using that formula, we would get cosine of 7 pi over 12 minus 5 pi over 12, which that's equal to cosine of 2 pi over 12, or cosine of pi over 6. And we all know cosine pi over 6, if we go back to that special triangle that we have right over here, we're going to get that cosine is adjacent over hypotenuse, which is root 3 over 2. And there's our answer. There we go. So I hope now by now you can probably see why we care about this. Like, why is this useful? It can give us a shortcut to all sorts of these equations. All right, now let's move on to example 3. Okay. So here it says if x and y are angles in this interval, where sine x is equal to 4/5 and sine y is equal to negative 12 over 13, evaluate cosine x minus y. So going back to our last page here with our formulas, cos x minus y was what again? Well, it would be cos x cos y plus sine x sine y. So let's write that down. Cos x cos y plus sine x sine y. Like that. Okay. So what is cos x and cos y? Well, we said that cos x, we're not sure. Okay, we're not sure actually, it looks like. But we do know what sine x and sine y are. Okay, we know that sine x is 4/5 and sine y is negative 12 over 13 because that's what they told us. However, from sine x and sine y, we can actually find cosine x and cosine of y as well, which is good. So if sine x is 4 over 5, and we know that x is less than or equal to pi over 2, that means that it must be in the first quadrant, right? X must be within that first quadrant. So it's going to be 4 over 5. Oh no, sorry, it's saying x is greater than or equal to pi over 2. So it would have to be in the second quadrant because 4 over 5, it's still positive, right? So we know that because 4 over 5 is positive, that means that this triangle here, the x triangle, would have to be in either quadrant 1, where all are positive, or quadrant 2, where sine is positive, because 4/5 is positive. Now, it says in our restrictions that x must be greater than or equal to pi over 2, or really what it says is that pi over 2 is less than or equal to x, right? But same difference, right? So that means our triangle must be here. It must look like this. And we know that if this is our x, right, our x degrees, we know that sine would be 4 over 5. So that means that the opposite over the hypotenuse is 4 and 5. So that means we just have to find this remaining value. Now, this is a classic 3, 4, 5 triangle, so it's going to end up being 3. But if I need to prove it, I will. Basically, our missing side, which we'll just call, what will we call it? We'll just call it A. We'll say A squared is equal to c squared, which is 5 squared, minus b squared, which is 4 squared. So a would be equal to the square root of 25 minus 16. So a is root 9, or 3. So therefore the answer is 3. And now that we know the triangle, we can figure out what is cosine of x. So cosine of x is adjacent over hypotenuse, which is 3/5. And also cosine is negative in quadrant 2, so it would have to be negative 3/5. So negative 3/5 is our answer for here. Now, what about cosine of y? Well, what's y? Sine y is negative 12 over 13. Now, we know that sine must be, it must be somewhere where sine is negative, so it can't be quadrant 1 or quadrant 2. It must be somewhere where sine is negative, so either quadrant 3 or quadrant 4. Let's go with quadrant 3 here because it also mentions here that y has to be less than or equal to 3 pi over 2. So that eliminates quadrant 4 as a possibility for these. So it has to not be that one. So it must be quadrant 3. So let's draw this in quadrant 3. And actually, I'll write my a equals 3 here because I want to draw it on the same diagram just for simplicity's sake. So I'm going to draw this triangle. And so now we have our full y degrees. And what is our answer here? Well, we know sine y is equal to negative 12 over 13, right? So sine would be opposite over hypotenuse. So the opposite would have to be negative 12, and then the hypotenuse would be 13. And that means that this, we'll just call it b, would be equal to 5 because this is a classic 5, 12, 13 triangle. Now let's say we need a proof of that with Pythagoras' theorem. We would know that b squared is equal to 13 squared minus negative 12 squared. So b would be equal to root 169 minus 144, which means b is equal to root 25, which is 5. So it would have to be 5. So knowing that b is 5, what is cosine of y, right? What is cosine of this angle? That would be adjacent, which is b, is 5, over hypotenuse, which is 13. And this actually is negative 5, right? It is negative in this quadrant for that reason, because we have a negative there technically, right? And so therefore, that's our answer. Well, almost. We're very, very close now. Okay, so if we multiply these out, we're going to get 15 over 65 plus negative 48 over 65, which is going to equal to negative 33 over 65, and that's our answer. Because keep in mind, we're not actually solving, we're just solving for cosine of x minus y here, right? We're not actually solving for a specific side, a specific angle that, might have the restriction of being positive. We're just evaluating this, and so this answer is perfectly good. And not only is it perfectly good, it's the correct answer too. Very good. Okay, let's move on to example 4. It says, use the compound angle formulas to show that sine of x minus pi, sine of x plus pi, and cos of x plus pi over 2 are equivalent. Now, we already know that they're equivalent from what we know about sinusoidal functions and the relationship between the parent function of sine x and the parent function of sine y, but let's show it the way they want using the trigonometric expressions. So let's start with number 1, which is sine x minus pi. So if we plug that in, we're going to get sine x cos pi minus cos x sine pi. Now, what is cos pi? Well, cos of pi is negative 1. This would be sine x times negative 1. And over here, this would be minus cos x times sine pi, which sine pi is what? Well, sine pi is 0 times 0. So this would just be negative sine x, and that's our answer. And that's the answer we should get for all of these if we're doing it right. Okay, so now let's do number 2, sine x plus pi. Well, if we plug that into our equation, we're going to get that that's sine x cos pi plus cos x sine pi. So what's cos pi again? It was negative 1. So we got sine x times negative 1. And then over here we get plus cos x times sine pi, which is 0. So it makes sense why these are equivalent, because the second part of this, the second term here just ends up being 0. And the first term ends up being the exact same. So therefore, we just have negative sine x, and we're done. And then we have 3. 3 is going to be cosine x plus pi over 2, which is equal to cos x cos pi over 2 minus sine x sine pi over 2. Okay. And what is cosine of pi over 2? Well, that's going to be 0, right? So we have cos x times 0 minus sine x times sine pi over 2, which what is sine pi over 2? That's going to be 1, right? If we think about our graph. So we're going to end up with 0 minus sine x, which is just negative sine x. So now we have shown that all three of these expressions are actually equivalent. They're all just negative sine x. They're just three different ways of writing the same thing using that formula. So that's another way that these identities can be useful. They can be useful in proving other identities that we need to prove for one reason or another. But yeah, that is it for today. Good work today, everyone, and I will see everybody next day. Bye, everyone.